present today, so let's get started right away with this. Next. Okay, here's the agenda for the presentation. We'll talk about the definition of a pharmaceutical isolator, since we will be talking primarily about pharmaceutical isolators. We'll do a brief comparison of traditional clean rooms and RABs versus isolators. We'll talk briefly about the different types of isolators. This is especially for those people that are new to isolator technology. Then we'll cover sanitization and vapor hydrogen peroxide, the main means to sanitize isolators. Then we're going to go through a process of building our own isolator, focusing on these 6 important aspects of isolators that you see here. And then we'll finish up with a brief description of the standard VHP cycle, and we'll go into a little bit of the development and validation of VHP cycles. So what is a pharmaceutical isolator? There's a lot of standards out there that have definitions for pharmaceutical isolators. ISPE has a definition, but I like the PDA. They're all pretty much the same, but the PDA definition is here. I won't read it verbatim, but it's a contained, decontaminated environment meeting grade A conditions. It's used for manufacturing. It provides uncompromised continuous isolation from of its interior from the external environment, and it can be decontaminated by a validated cycle. It's used primarily in the production of sterile products, and it has a continuous supply of overpressure air, HEPA filtered air. So let's talk about the evolution of aseptic processing. You see here a traditional class 100 area where the operators are gowned in sterile garb. Traditional class 100 clean rooms started in the early 50s and advanced through the 1980s, but there have really been no significant changes or improvements in the traditional class 100 clean room since the 1980s. Then in the evolution of aseptic processing, RABs, or restricted access barrier systems, were introduced, and these were really just shrouding around the sterile, the core, or where the sterile manufacturing was taking place. And there's 2 types of RABs out available today. They're open and closed. And open RABs is really just that. They're doors which close around the aseptic area. These doors can be opened for the operators to lean in to make interventions and to work on the system inside. Then there's closed restricted access barrier systems where the doors remain largely closed through the entire process. Operators may be able to access the inside through glove ports. And then the introduction of isolators took place really in the early 1980s, appearing primarily as sterility test chambers, but their success in that area in preventing false positives led to their introduction and acceptance into aseptic processing. In the past 40 years have been dramatic improvements in controls, ergonomics, cycle times, and then the lead times and the costs of isolators have been reduced dramatically as well. So let's take a look at the difference between an isolator and a traditional clean room and RABs. You see here on the left an isolator, and on the right you see a traditional clean room, people gowned. The biggest difference here is in the sterile gowning. In a traditional clean room or a RAB system, operators must sterile gown. They're fully covered. There's a lot of training that goes into training an operator and how to do the sterile gowning. There's a lot of plating that's required. And essentially the operators have to be validated in how to don their sterile gowns and goggles and how to perform operations in a sterile environment. These are typically relatively uncomfortable, and they can lead to a lot of sweating of the operators. In the isolator system on the left, you see there's a very simple gowning of the operator there. They're just gowned in scrubs. There's no plating of the operator, and there's great comfort. So the background in a traditional clean room in a RABS environment has to be a grade B background. A grade D is all that's required in many isolator systems. In a traditional clean room, the operator can be in close contact with the product, and in an isolator, the operator is well separated from the product. Another large advantage here is that the sanitization in a clean room with wet chemical sanitizers can lead to a 3 to 4 log reduction, while in a RABS using a gaseous sanitizer, you can get greater than a 6 log reduction of the bioburden in there. And also that 6 log reduction is very reproducible sanitization because it is a gas that contacts all surfaces, where in a traditional clean room RABS, the cleaning is really personnel dependent. Did they get all the areas they were supposed to? Did they miss something? So briefly, the types of isolators, there's many different ways of looking at these by barrier type. There's closed isolators. This is an isolator which is completely sealed during operations with the material transfer in and out via aseptic connections. There's open isolators that have specific opens for material transfer in and out of the isolator. Openings are engineered to prevent the entry of contamination from the outside of the isolator through the use of overpressure and other tools. Isolators can also be classified by their size. There's single chamber isolators with a pass box, which is just a small box which allows for a rapid decontamination of materials to be passed into the isolator. There's multi-chamber isolators. Isolators can also be coordinated or integrated with a lot of other equipment, such as autoclaves to unload sterile material directly into the isolator, depyrogenation ovens and tunnels for glass, and lyophilizers for freeze-dried drug product. Isolators can also be classified by the specialized, the specific functions that they take place. There's sterility test isolators, which one is shown here. This chamber that I'm showing right here is where the sterility test would be performed. This is a rapid decontamination pass box to get materials into the sterility isolator. There's sterile filling isolators. This is one at BSM. This is a multi-chamber isolator. This first chamber here is for the introduction of the glassware that's being used. This chamber is where the filling takes place. And this is a RAB system that houses a capping system to perform capping of liquid vials. There's sampling isolators like the one that is shown here. This may be used for sampling potent compounds to protect the operator from the compound, or can also be used for aseptic sampling to protect the product from the operator. There's compounding or formulation isolators like the one that's shown here. Again, they can be used for sterile aseptic formulations to protect the product from the operator, or they can be used with very potent compounds to protect the operator from the product. Now let's talk about sanitization and disinfection in isolators. Isolators can be sealed and sanitized by a gas or a vapor, leading to a very high level of disinfection. Gaseous vapor sanitizers are used in isolators. Here are some of the sanitizers that we use, or currently use: hydrogen peroxide, ethylene oxide, nitrogen dioxide, and chlorine dioxide. In early days, formaldehyde and peracetic acid were used, but they led to very long sanitization and aeration times, so they've fallen out of favor. By and far, hydrogen peroxide is the most commonly used sanitizer in pharmaceutical isolators today. So all sanitizers work by oxidating proteins, nucleic acids, nucleotides, and other biomolecules, leading to cell death. And again, a significant advantage over RABs in traditional clean room is a 6 log reduction versus a 3 to 4 log reduction of bioburden that you'd see in a traditional clean room with wet chemical sanitizers. Gaseous vapor phase affects all exposed surfaces and is not dependent upon the cleaning operator's performance. However, you do have to be aware of occluded and mated surfaces. If materials have to be hung in such a way that there's enough space in between them for the gaseous vapor to get to cause the sanitization. And large objects which may be mated to the floor may have to be lifted up off of the floor with with basically dollies or round cylindrical tubes to lift them up off the floor so the sanitizing solution can get underneath. Why vapor hydrogen peroxide has become the #1 of choice? It's readily available. There's many years of experience with it as a sanitizer. It breaks down into water and oxygen, so there's no residues left after the sanitization and aeration is completed. Exposure times are reasonable. They can be aerated fairly quickly. Exposure times can range generally from 10 to 50 minutes, depending upon the size of the chamber and the materials in it to be sanitized. Aeration can be anywhere from just a few minutes to a couple of hours, again, depending upon the complexity of the system. Hydrogen peroxide is less toxic than many of the other agents, and it's also compatible with many materials. So let's talk about the VHP process a little bit. The vaporized hydrogen peroxide is produced from typically a 30 to 35% liquid hydrogen peroxide, which has a boiling point of about 108 degrees C. It's heated to approximately 110 degrees C, evaporating the hydrogen peroxide and the water before being introduced into the isolator chamber, where the temperature normally is about 25 degrees. In the chamber, the hydrogen peroxide and water are in equilibrium between gaseous and liquid phases, which is dependent upon the local temperature. The temperature at 25 degrees C favors the majority of the water and hydrogen peroxide being in the liquid form rather than in the gaseous form. So H2O is likely present on the surfaces in a micro condensation with water, a very thin layer of liquid that is visible to the eye. This is in what's called a dry VHP cycle. The sanitization action is primarily due to liquid phase hydrogen peroxide, not gaseous hydrogen peroxide. Decreasing the temperature and increasing percent relative humidity will lead to visual obvious condensation. Higher temperature areas experience less sanitization action. That is because they can hold more water in the air at higher temperatures. So the percent relative humidity in those areas is actually lower, so you get less hydrogen peroxide put on the surface. And recently there's been a lot of discussion about wet versus dry cycles. In actuality, all vapor hydrogen peroxide cycles are truly wet cycles. The quote dry cycles appear dry. That's because there's a very thin layer of water on the surface with the hydrogen peroxide in it. It doesn't appear wet, it appears dry. And visual condensation is to be avoided. That's a question. The jury is out on that. Typically in dry cycles, you do want to avoid visual condensation because you start to lose control of your VHP process. But you can design cycles which are specifically designed to be wet, where you'll see visible hydrogen peroxide, visible condensation inside your isolator. Okay, let's build a simple single chamber isolator. So what we need is a chamber. It's basically a sealed box with a window, which you see here on the right. And then we need to add to it some glove ports so the operators can get into the chamber and operate and perform the tasks they're supposed to. So we'll put a couple glove ports right in the front here. Then we need an opening or a mouse hole, a way to get materials in and out of the isolator. So let's put that over here on the side of the isolator. The next thing we need is HEPA filters. We need a unidirectional airflow from the top of the isolator to down to the bottom of the floor. And we'll may need some HVAC. We're going to need some fans, but we'll put those right up here in the ceiling of the isolator. Then we're going to need a vaporizer, some way to produce the vaporized hydrogen peroxide to go in there. We'll put that up on top of the isolator over here. And then we need a sensor, something that can measure the vapor hydrogen peroxide to let us know the progress that we're making in our cycle. So here we have it, voila, a simple isolator. And here is a simple single chamber isolator at BSM. This is 6 glove ports, but it has all of the features that we talked about here. This that you see on the left is a RABS unit for passing RTU containers into the isolator. Now let's talk about each of these in a little more detail. The chamber is sealed, and it's typically vacuum leak tested during the FAT or SAT or OQ. And there's ISO guidelines which speak to the classification of the chambers based upon their percent volume loss over a unit of time. They're listed here. I won't go into a lot of detail. You can read all of this information. I just want to point out the two that are most commonly used in the pharmaceutical industry are shown here. We're going to be focusing on probably the most common, which is a positive pressure aseptic isolator, which can have a percent volume loss of up to 1% per hour. Now, what else do we expect from the chamber? Well, ideally, it should be compatible with and non-absorptive to hydrogen peroxide. You don't want something that the hydrogen peroxide is going to corrode, and you don't want hydrogen peroxide to be absorbed to the surface because that's going to take a long time for aeration. The dimensions of the chamber have to be appropriate for the use. You have to be able to fit the equipment that you need inside. You need room to hang required plates, tools, utensils. It should be ergonomic so the operators can reach to the areas and the tools inside that they need to. It needs to be easy to clean and to pre-sanitize. And pre-sanitization is very important. We'll talk about this a little bit more later. Very early isolators were mainly of flexible films and plastic. The majority of pharma isolators now are stainless steel and glass. Now let's talk about gloves and glove ports. Glove and glove ports are often given the least amount of attention in an isolator, and this is a terrible mistake if one does do that. Failure to install appropriate gloves and glove ports can lead to glove integrity failures, chemical incompatibility, long aeration times, and other problems. It used to be that companies operating isolators would perform glove integrity tests to demonstrate the integrity of the gloves on a periodic basis. It might be weekly or biweekly, but now regulatory expectations are that glove integrity tests should be measured before and after every activity in a filling isolator. So if you're conducting a filling operation, you're expected to have glove integrity tests done immediately prior and then immediately after that operation. Okay, glove ports should be placed for good ergonomics. They should be gentle and compatible with the gloves that are going to be installed in them. They should be designed for ease of integrity testing, for use with compatible glove extenders, for easy glove replacement. And it's important that they allow for the full integrity testing of the glove, not just a portion of it. Something I should point out is it's extremely helpful if you have multiple isolators in a facility to have a universal glove system. At BSM, we had 3 different isolators, all had different glove ports, different glove extenders, and different glove integrity testers. We standardized all of that, so there's one type of glove port and one glove that's used in all of the isolators throughout the facility, and our new isolator line, which we're taking delivery of late this year, will also have that same. That way we're able to use the same glove integrity testers on all of the isolators, and we only have to purchase and maintain inventory of one type of glove. Glove integrity testing is extremely important, and we're going to talk a little bit about that. What I have here is a picture of a glove port on an isolator. Part of it is mounted permanently on the isolator, and then part of it can be taken off to put a glove on, remove a glove. It's very important that this be done correctly. If you look at this drawing over here, this is the glass window. This is the piece of the glove port that's attached permanently to the glass window, and this is the piece of the glove port that's attached to the glove. Hold on, trying to get one thing to show up here. Okay, it apparently didn't make it into the slides. What I did was, this area here was highlighted. You see that I'm moving the mouse around because this is the part that's attached to the glove. And you can see this is the bead where the glove bead goes right here. And it's important that the glove integrity tester seal here. And so you're getting a full glove integrity of the glove and also this connection here with the side of the isolator. I have seen some glove systems and glove integrity test systems that actually seal on the inside of the glove and don't give you full integrity of this area right in here. So it's very important that you pay attention to the type of glove tester that you're using. With one of our isolators that we brought in, we had a problem that we were occasionally getting glove holes in the collar up around the shoulder area of the operators after operation. And we did a lot of work and a lot of investigation and found out that it was really due to the glove and glove port not being matched correctly to one another. I must point out that all of the isolator manufacturers, I think, do a very good job making isolators, but some of them give less attention to the glove ports. Looking upon that, I think, is a necessary evil and not something that's really part of the overall isolator. These are some emails, some comments from emails from Steve Chungalo of MK Metal Free talking about the importance of the fit of the glove with the glove integrity test, with the glove port. A properly designed port takes the size of available gloves into account and ensures that the ring that the bead and the glove stretch over are no more than 18% of the diameter of the glove cuff. So it's very critical that you pay attention to the combination of your gloves and your glove ports. Gloves. The length should be appropriate for the use in the isolator. The operators need to be able to reach to certain equipment to do their job. Then the glove needs to be able to reach to that. You don't want the glove to be too long because it gets too loose and kind of sloppy for the operators to work with. Also, you don't want the glove to be so long that when you extend it for the VHP process that it can reach across the isolator and touch the wall on the other side, because then you get occluded surfaces, two surfaces pressed up against one another where you can't get good distribution of the vapor hydrogen peroxide around it. Material construction is important. Some common materials are shown here. CSM, trademarked as Hypalon, is a very common one. At BSM, we're using this Isoflex XSBR, which is a carboxylated styrene butadiene rubber. There are both two-piece and one-piece glove systems available. I'm not a fan of the two-piece glove system because an operator can, if they push too hard, push a glove off. We use exclusively in isolators one-piece glove systems. And something that should be pointed out in the use of gloves, operators must use sterile gloves inside the isolator gloves and sanitize them frequently. This is now a regulatory, excuse me, this is a regulatory requirement now, and it is actually in some of the standards that sterile gloves be used inside isolator gloves. Glove integrity testing. It's a regulatory expectation that this will be performed, as I said before and after every run. Any glove integrity failure should be investigated as a deviation and should include a risk assessment of the potential risk to the product that was being produced. Glove integrity tests are usually visual, which is not very sensitive, and a pressure decay detection, which is sensitive to 100 to 150 micron hole or larger. New modern systems can detect glove failures quickly, can be wireless, and can test multiple gloves at a time. We had an isolator, or have an isolator here that the isolator company supplied an integrity test system with the isolator. It could run 2 gloves at once. We had 18 gloves in the system. It would take us a minimum of 20 minutes per glove. So it would take us up to 6 hours to complete all of the glove testing on that system. We replaced it with a new modern wireless system that can test multiple gloves at the same time, testing 8 gloves at one time. with a very quick cycle, less than 7 minutes to detect the holes. We were able to get that time down to less than 1 hour. Another very critical thing about gloves is that a recipe or a program is required for every glove size and material. Glove integrity testing, it does use pressure decay. Gloves are inflated to a certain pressure, usually around 1200 pascals. They're held for a stabilization period, and then they start measuring the pressure decay over time. And you can see here on this top line are Isoflex gloves. These are all intact gloves. They have about a 45 pascal decrease or decay of pressure over 10 minutes. This is a CSM glove right here. You can see they have approximately 135 pascal decay over a 10-minute period of time. So it's very critical that you base your decay curve and your glove integrity testers on the particular glove material and size that you're using. For instance, if you used a Isoflex recipe with a CSM glove, you would find that even an intact CSM glove would always fail. Conversely, if you use the CSM glove recipe with an Isoflex glove, you could find that a failing Isoflex glove down here would still be above the decay of a intact CSM and would give you an acceptance. So you'd have a false negative result there. I want to briefly mention gloveless versus operatorless systems. There's been a lot of press recently about gloveless isolators, and they claim that they eliminate all glove failures. And of course they do, because you don't have gloves, so how can a glove failure? However, these require dependence upon the equipment to be free from any failure that would require an intervention. And I think maybe this is good with very established lines, but if you're doing a lot of different manufacturing, as we do as a CMO, this is a little difficult to believe that that would always be the case. Glove failures, if you appropriately choose your glove and your glove ports and you replace them on a periodic basis, the failures are almost exclusively due to misuse by operators. So an isolator with gloves that are not used provides the same protection as a gloveless isolator, but with the opportunity to respond to an equipment failure should one arise, which is why at BSM we use only isolators with gloves, but we do have some systems, or the new system we're purchasing, that will be running purely robotic, so it shouldn't require much intervention from operators at all. Here's an example of a multi-glove glove integrity tester on an isolator. You can see the isolator door is open. This is at the end of a manufacturing run. They're testing 3 gloves simultaneously here. The gloves are inflated. You just slip the glove integrity tester in, press the start button, in approximately 7 minutes, it gives you a result. This is what you see on the HMI for the glove integrity tester. This shows all of the glove ports on the isolator. The ones in green have been tested and passed. The ones that are white have not been tested yet. And this system won't let the operators progress into the next stage until they have a passing result of all gloves on the isolator. Now, openings, sometimes known as mouse holes, let's talk about those real quickly. You need methods for ingress and egress of components and products, especially for larger batch sizes and higher speed fill lines. Mouse holes are closed during sanitization and aeration processes. An airtight seal is typically achieved by a pneumatic bladder seal. Sizes are made to accommodate the materials that moved in and out of the isolator. Airflow in an isolator must be from inside the isolator to out. Overpressure in the isolator is a minimum of 10 pascals by many standards over the room that this isolator is contained in. However, in practice, most isolators run with much higher pressure, typically 17 to 50 pascals. Types of mouse holes is active mouse holes. This is a mouse hole that opens and closes during aseptic processing. A passive mouse hole is one that remains open or closed through your aseptic processing. And with mouse holes, you should also consider additional means to protect the mouse holes from external environment. At BSM, we have RABs in front of every single mouse hole entry and exit to ensure that there's no chance of any contamination getting inside the isolator. Here's a picture of a passive mouse hole. This is in a RTU filling. It's actually a flexible filling line, but this is the introduction of RTU containers. So the tub would be passed through here. We're looking from a RABs into the isolator here, and you see the isolator glove. This is the cover, which goes on the mouse hole. This is the bladder seal here. So this cover is placed in here. It locks on these pins. The sensor here senses the presence of the mouse hole, and then the operators from the HMI can inflate the bladder to make the seal. This is a picture of a manually active mouse hole. You can see this is the mouse hole here, the glass, the seal that's made here, the bladder is actually contained within the isolator and not on the cover. So the operator from the HMI can deflate the gasket, then open the door, put materials in or take materials out, whichever is being done. When they close the door again, the gasket automatically seals. Okay, the HVAC system, we know that we need a laminar flow or we need a flow of air through HEPA filters to produce the grade A air that's being used inside. Usually the air recirculates through a plenum with some exhaust and some makeup air, or you can get systems that have 100% exhaust and 100% makeup air. You can have unidirectional or turbulent flow in an isolator. Turbulent flow is acceptable in some cases by some regulatory authorities. In fact, the FDA states in the 2004 sterile manufacturing guideline that turbulent flow can be accepted within closed isolators, which are normally compact in size and do not house processing lines. An example of this is sterility isolators. There are sterility test isolators that use turbulent flow. But by and large, unidirectional airflow is more common and expected specifically in aseptic processing isolators. And the universal, 0.45 meters per second, or about 90 to 100 feet per minute, is what's generally used for the unidirectional airflow. Okay, here's an isolator. This is a single chamber isolator that I showed you before. We'll look a little bit at how the airflow operates in here. We're looking at the ceiling of the isolator right here. Above this stainless steel grid are the HEPA filters, and the air is being blown down through these HEPA filters in a unidirectional manner. While we're on the screen, I wanted to point out a couple of other things. This is where the vapor hydrogen peroxide is introduced into the chamber. And this little grated area on the wall here, there's actually a fan behind here, which comes on during the VHP process to help distribute the VHP throughout the chamber. This is the floor of the isolator. You can see it's perforated, so the air is coming unidirectional from the ceiling down through the floor. And underneath the floor, we have ducts and then a fan that captures the air and puts it back up to the plenum up above. This is the return duct right here and here for that isolator. This isolator actually takes air out of the clean room. So this is where the makeup air comes in right here. Okay, small isolators can often take air directly from a clean room and can exhaust to the outside. That's the isolator that I just showed you. Large isolators, however, may require too much air, which would cause a drop in the room pressure if the air is taken from the room and it's not returned to the room. Also, large isolators, because they have large fans in them, can produce too much heat and require air conditioning. If outside air is used, chilling, and rehumidification and heating will be required. And pressure balancing of clean rooms can greatly be impacted by isolator operations. We've had in installing isolator situations where a small isolator actually dropped the pressure in the room because it was taking too much air, so we had to go and rebalance the clean room. We also have a large isolator that takes 100% outside air and exhausts all of that. But when the mouse holes are open, air is coming out of the mouse holes into the clean room, and we actually see the pressure increase in that room when the isolator is in operation. Let's talk about vaporizers really quick too. A vaporizer produces the vaporized hydrogen peroxide. Liquid hydrogen peroxide is pumped into a heated chamber about 110 degrees centigrade, where hydrogen peroxide and water is evaporated. Compressed air supplied to the vaporizer carries the gaseous hydrogen peroxide and water to the chamber. And lines carrying the VHP should be very short and insulated or heated to avoid condensation in the lines to ensure that all of the vaporized hydrogen peroxide and humidity of the water gets into your isolator. I'm going to show you a couple of examples of vaporizers here. This is from a Steris M10 unit. This is really very simple, even though there's a little bit of electronics. It makes it look a little more complicated than it is. This is essentially just a graduated cylinder back here that fills up with liquid hydrogen peroxide at the beginning of the cycle. And then that liquid hydrogen peroxide is pumped by a small peristaltic pump, which is right here. You can see this is the line coming into the peristaltic pump, and this is the line going out. The line going out goes into this vaporizer here, which is essentially just a large stainless steel can that has a heating element in the bottom, and the vapor hydrogen peroxide is dropped onto that heating element, and it evaporates. And then air provided by the system then pushes through here, grabs the hydrogen peroxide and water, and puts it into the chamber. Here's another vaporizer. This one's a little more complicated, a little more sophisticated. This vaporizer here has a preheater for the air coming in. This is the preheater that preheats the air coming into the system. The air then is pumped into the vaporizer here, and it's hot air. On top of the vaporizer is a small diaphragm pump. That's this right here. The diaphragm pump is pumping from a reservoir. You can see, follow the line back, which is up over here. That pump then pumps into the vaporizer, which again is just a heated plate on the bottom that evaporates the hydrogen peroxide and water. And then that goes into the chamber through this stainless steel line here, which is insulated. It's a very short line into the chamber. This is a multi-chamber system, and each chamber has its own vaporizer on it. Here's a synoptic of the vaporizer in operation, which will probably give you a little bit clearer picture of what goes on. This is the reservoir that the hydrogen peroxide is maintained inside. It was set to start off with 250 mils. It's at 240 mils right now. The pump is on. This is green. This is the preheater here where air comes in. The preheater is set between 75 and 80. It's currently at about 71. The air line is open, so it's blowing air through the vaporizer and the liquid coming in. The vaporizer temperature is set at 110. It's at about 104 right now. And this is displaying the VHP level inside the chamber that it's feeding. It's at 438.7 ppms of vapor hydrogen peroxide. Okay. Sensors are necessary. They verify the VHP levels inside, that you can see that you've achieved the correct level, and necessary, of course, for validation. Most isolators employ high and low range sensors. High range sensors can become saturated and then take time to aerate, leading to longer aeration times. Low range are employed only after levels of a high range drop to a predetermined ppm value, usually about 50 to 75 ppms. The high range dragger shuts off, and then the flow is diverted into the low range dragger to follow the end of the aeration cycle. Low range sensors are more accurate for low VHP levels. They aid in determining when it's safe to use the isolator, usually 1 ppm or less. The 1 ppm is not a totally arbitrary number that was selected for most of these. That is the OSHA exposure limit for extended exposure to vapor hydrogen or hydrogen peroxide. Let's now get into the VHP cycle. There's 4 standard phases to VHP cycles. There's a preparation or a dehumidification phase. This adjusts the temperature and or humidity levels. Then there's a conditioning, which introduces VHP to achieve high levels to start the sanitization. Decontamination then maintains the high level of VHPs at sanitization levels for a fixed period of time. And then aeration, once decontamination is done, air is pumped into the system to remove the VHP to predetermined levels, as I said before, usually less than or equal to 1 ppm. As I mentioned before, pre-cleaning and sanitizing, pre-sanitizing of the isolator is very critical. Isolator must be thoroughly cleaned to remove all residues and deposits. We should point out VHP in an isolator is a sanitization process, not sterilization. So if you have a surface with a residue on it and you have a spore or bacteria trapped under that residue, it's very likely that that spore would be protected by the residue on top of it, and you won't achieve sterilization or good sanitization. So it's very critical that the isolator be cleaned thoroughly and there's no residues left on it. It should also be pointed out that all product contact parts must be separately sterilized and hung or placed in the isolator. I have heard of some companies leaving stopper bowls in and using a sanitization of the isolator to, quote, sterilize the bowl. That is not a good practice and should be avoided. All product contact parts must be sterilized. Large items that need to be placed on the floor because they can't be hung, such as stopper bowls, can be placed on dowels to avoid mated or occluded surfaces. And gloves must be fully extended with no folds in them, so you can ensure that the sanitizing agent hits all surfaces of the gloves. Belts, conveyors, and shafts should be running during VHP, again, so all surfaces get exposed to the sanitizing agent. Now let's talk about the preparation phase. More sophisticated single and multi-chamber isolators will adjust temperature usually to about 25 degrees centigrade. Simple single chambers use room temperature. When this is the case, the room temperature should be tightly controlled. Humidity. Humidity is reduced to a consistent starting value, usually about 20% relative humidity. If you start off, especially with dry cycles, with the humidity too high, you're going to get condensation and not the cycle that you would hope to in there. 2 standard methods of drying or reducing the humidity is to use a chemical desiccant or the use of dry compressed air. And here's an example of a desiccant. This is, again, Steris M10 VHP equipment. This is the desiccant cartridge right here. This is a disposable one. It can be used once or twice and then disposed of. We also have regenerated ones that we can use in here as well. This right here is a bottle of hydrogen peroxide that's been put onto the system. And then our larger isolator uses dry compressed air with a dew point of about -40 Fahrenheit in order to dry out the chamber before starting with the conditioning phase. Now, conditioning. Generally, conditioning is 5 to 15 minutes. It's rapid introduction of hydrogen peroxide to get VHP levels to that required for the contamination and sanitization. During this phase, VHP and humidity increase rapidly. And then we move into a decontamination. The hydrogen peroxide is pumped into the vaporizer, but at a much slower rate to maintain the desired VHP level in the chamber. Pump control. There are some systems that just utilize continuous pumping, but at a slower rate during decontamination than during the conditioning phase. Validation determines the pump rate required in each of those phases. There are some systems that have VHP sensor feedback to control the pumping. So you achieve a certain level of VHP, the pump stops pumping until the VHP level drops again, and then the pump will start pumping again. Large multi-chamber units may use feedback from, may use a centralized system vaporizer then that feeds all of the chambers, but it modulates valves controlling the amount of VHP in each chamber, or some of them use separate vaporizers for each chamber. And the percent relative humidity is maintained very high, close to 100%, so you get the best distribution of water and hydrogen peroxide on the surface. VHP introduction can be performed with or without air circulation through HEPA filters, that is dynamic or static. VHP can be introduced above or below HEPA filters. If above, the fans must run through the HEPA filters to circulate the VHP to the area down below the HEPA filters. If static, fans below the HEPA filters or other devices can be used to help distribute VHP, but are often not necessary. Our larger multi-chamber system here is a purely static system, and there's no fans inside to distribute the vaporized hydrogen peroxide. It's just sprayed into the chamber. But I showed you the smaller chamber that we had. We have experience with all of the systems above and have successfully validated all of them. But this is the chamber that I was showing you earlier with the fan to distribute the vapor hydrogen peroxide inside the isolator. Okay, here's a schematic of a typical standard VHP cycle. This is the preparation of conditioning, dehumidification. You can see here, this is the temperature. The temperature is being increased to a certain set point, 25 degrees centigrade. This is in Fahrenheit, so I could use the same graph over here. And then this is the humidity inside the chamber, relative humidity. So the percent starts off at about 50% relative humidity. It goes down to 20%. Once the temperature and humidity are maintained at the preset levels for a period of time, it will start the conditioning phase where the VHP is pumped into the chamber and the VHP levels increase very rapidly, and also the humidity levels increase very rapidly. Then once you've achieved the set point level, in this case it's 800 ppms, you pretty much plateau and hold that level of VHP and a very high level of humidity for a set period of time. Once that's done, we go into aeration. We stop pumping vaporized hydrogen peroxide and turn on the fans, start pushing air through the system. This is typically exhausted to the outside. You'll see the VHP levels drop very rapidly. Also, the humidity drops rapidly, and the temperature will drop rapidly. You may see a slight increase in temperature during the conditioning and the decon, because you're spraying in a hot vaporized hydrogen peroxide and water gas. Okay. Here's some pictures of an isolator ready for vapor hydrogen peroxide. You can see all of the materials are hung inside the isolator. There's space in between all of these, so the vaporized hydrogen peroxide can get between these and can sanitize all surfaces. These are the gloves. You see they're fully extended right here. And here's a picture of VHP off of our HMI. This is a multi-chamber isolator. We're looking at just chamber number 2 right now. There's about 45 minutes from the start of the cycle to get to the conditioning phase. The drying here took a long time because this takes outside air to use in the system. And you can see this was done in August when humidities are very high, so it took a relatively longer time. Sometimes in the winter, we don't even have to go through a drying phase. The air is so dry coming in that it goes right from adjusting the temperature and turning the fans off then into a conditioning without dehumidification. So this is where conditioning takes place, very rapid increase in VHP. Then you hold the level at the sanitizing amount that we want. And then when the cycle's done, we go into aeration and you see the VHP level drop. This is what the humidity curve looks like on the same. Again, this was adjusting the temperature to be where it's supposed to be. Then it goes into a dehumidification phase here. You can see the humidity is dropping. We start conditioning, humidity climbs very quickly. It plateaus at just a little bit over 100% during the decontamination. And then when you go into aeration, then the humidity starts to drop back down to the 50% level that's desired in the isolator. Again, multiple chamber isolator here. This is the VHP curve for each of the chambers in the isolator. You can see each chamber has a different level. That's dependent upon the size of the chamber, the materials that are hung in it, and other parameters. Environmental monitoring. Just as in a traditional clean room, environmental monitoring must be performed. Non-viable is performed at critical locations during operations. Viable can be performed periodic near critical locations or continuous. Plates that you use should be validated for exposure to VHP. You want to hang your plates inside your isolator so the outside of those wrappings are decontaminated before you open them in the isolator to take the plates out and use them. You need to go through a validation process with your plates to verify that they didn't absorb a lot of vapor hydrogen peroxide in the process and then would be giving false negative results. Another thing that we found is that plates that are used should be placed in sterile containers before being passed out of the isolator. We did have a period of time where we had a couple of positive hits inside the isolator, which was very surprising. We identified two potential sources of that. One was the handling of the plates. They were being passed out of the isolator and then being put into bags, labeled, and taped outside of the isolator. When we stopped doing that process and putting them in sterile containers before they were passed out of the isolator, we found that it totally eliminated any positives that we were seeing. We've gone more than a year and a half since that date, and have seen no positive growth inside the isolator from our EM monitoring. Surface monitoring needs to be conducted at the end of the activity before opening the isolator. That's all gloves, critical surfaces such as fill needles inside stopper bowls and other places that you determine are critical. Glove integrity tests must be performed. Okay, validation of VHP cycles. A little bit on BSM's experience here. We've run only the dry VHP at BSM. We found that 700 to 1,000 ppms of vapor hydrogen peroxide for 30 to 50 minutes is necessary for a 6-log reduction of geobacillus. Humidity is important, and the closer to 100% the relative humidity is, the faster the kill. BI should be placed in warmer locations, and you should use temperature mapping of your isolator to identify those warmer locations. Typically, those warmer locations are going to be right near where the vaporized hydrogen peroxide enters the chamber, because you've got a hot stream flowing into the isolator. Okay, and validation includes empty chamber challenge with BIs and CIs. Chemical indicators are important to help to understand the distribution of the gas. We typically start off with chemical indicators to look at distribution of the vapor hydrogen peroxide throughout the chamber, and then we'll introduce BIs in the areas where we see the least amount of vapor hydrogen peroxide. Full chamber with BIs and CIs is also performed. This is with everything that you'd put into the chamber hanging inside the isolator, and with BIs and CIs on all of the materials that are hanging from the isolator. rogue BIs can be a problem. Therefore, one should use multiple BIs per location. And we'll provide more information on this in the next webinar. This has been a subject that's there's been a lot of publications on recently. So at BSM, we've had 3 different isolator manufacturers. We've got a 4th one we're working with now, each with a different approach to VHP distribution systems, different controls of VHP levels, but all have been successfully validated. So a thought for the day. If you buy a car, you don't go for the 1980s technology. You don't go into the showroom and say to the salesperson there, yeah, give me the best 1980s technology you have. No, you're going to look for the automatic emergency braking, the rear view camera, parking assist, GPS, remote start, and the turbo economy engine. When I was in Germany and Italy in early 2020, just before COVID hit, I was evaluating different isolator suppliers and looking at various technologies. I toured a lot of them, and there were a lot of isolator production going on the manufacturing floor, but there was almost just as many RABS system being produced for standard clean room systems for aseptic processing. So if you wouldn't purchase a 1980s traditional clean room and or RABS to produce your sterile product, why would you when a much better technology exists today? So that concludes my presentation. I'm sorry, it was a lot of information very fast. I hope it was helpful to you all. I want to thank the New England chapter of PDA for giving me this opportunity to present this information, and I'd like to thank you, the audience, for attending this webinar. And helpful publication on isolator practice can be found here. This is a very recent publication by PDA 2020, so it's really very recent, and it contains a lot of great information. I suggest if you're interested in isolators, that you take a look at this and you find out a little bit about standard industry practice from that as well. So it's points to consider for the aseptic processing of sterile pharmaceutical products and isolators. Thank you.